Hi, I'm Anthony Edgar.
Hi, I'm Nathan Grubb.
I'm William Walker.
Hi, I'm Matthew Biddle.
And I'm Jesse Lynch. Tonight on 15 Minutes, Lithium Polymer Batteries.
Batteries have been powering mankind since the 1700s. Their first batteries were the size of a barrel, and today, they're the size of, they could even go down as far as the size of a penny. They powered medical devices and personal electronics like this. Tonight on 15 Minutes, we're going to learn about how the drum-sized battery got to these size batteries, and how polymers are a part of that world. The first battery was invented in 1800 by Alessandro Volta, an Italian scientist. Now, he stacked zinc and copper plates on top of each other, and in between those, a cloth soaked in brine solution as the electrolyte, and a wire connected to the top and the bottom of this voltaic pile allowed an electric current to flow. Now, the basic chemistry of batteries follows like this. There's an anode, a cathode, and an electrolytic solution that facilitates electron transfer. The anode it basically follows an oxidation and reduction reaction. The anode gets oxidized, and as it ionizes, electrons migrate from the anode to the cathode, where reduction takes place. And the copper ions in solution, in this case, would turn into the copper metal as they receive those electrons. The problem is that this generates hydrogen gas, so we'll see how batteries have developed in the future to address this problem, and how polymers have solved that issue. Scientists over the years have expanded upon Volta's design, the voltaic pile. The Daniell cell, designed in 1836 by a British chemist, used a second electrolyte to absorb the hydrogen gas. And a French chemist invented the gravity cell, which became the standard in the telegraph industry. And eventually, the first rechargeable battery, the lead-acid battery, was invented in 1859. And the basic concepts are still used today in automobiles. The 1900s revealed some significant changes in the battery industry. The common alkaline battery was invented in 1955, and batteries were finally made inexpensive by using manganese dioxide cathode and a powdered zinc anode. And nickel metal hydride batteries in the 1980s were invented because they have a longer lifespan and they're actually used in satellites. Now, these batteries that we just discussed have significant limitations. They have low energy density, they're high maintenance, and have very short shelf lives due to their high self-discharge rates. And they're very heavy, and their shapes can't be altered into anything useful, like that go into our phones. So what scientists have invented are lithium-ion batteries. And these batteries really are the future. And until now, all the electrolytes have been in an aqueous solution, and we'll see that the future is with lithium and with polymers as the electrolytic source.
So why is lithium the answer for now and the answer for the future? You might be asking, why Li? Well, to answer this question, first we need to look at the what. So what exactly is a lithium-ion battery? A lithium-ion battery contains a liquid electrolyte using lithium ions and two solid electrodes, usually carbon and metal oxide. Now, lithium is important in this equation because a lithium has the highest electrochemical potential out of all of the other components, especially metals. Lithium is also the lightest metal. These two things combined creates a very high energy density, which is crucial and even ever more important as technology strives to become lighter and smaller. Furthermore, lithium offers the broadest range of operating temperatures where you can discharge that electric potential, which is highly useful for many applications of batteries. Now, some of you may be out there wondering, why are we talking about all these metal ions in a polymers class? Well, that brings us to the real meat and potatoes of our discussion here tonight. And that is to talk about lithium polymer batteries, polymer being the key word. So even though both of these types of lithium polymer batteries go by the same name, they are two distinct, separate strategies to making the electrical current flow. The first involves a solid or gel polymer electrolyte, in which the polymer itself is in the electrolyte, and it's a porous substance that allows the ions to exchange from the cathode to the anode. On the other side of the battery coin, you could say, is the polymer casing battery. In here, the polymer is the actual shell that encases the battery, or it could also be seen as a pouch where it's more flexible material. These two types of batteries also have their own advantages and disadvantages that go along with them. For example, the solid gel polymer electrolyte battery, the traditional lithium polymer battery, can fit many shapes and sizes because the electrolyte now can be in the solid form and can contort to many different configurations. In the same manner, the potential for leakage is almost eliminated because there's no longer a liquid electrolyte solution as there would be with the standard lithium-ion battery. On the other end, you have the LiPo battery where the polymer is in the shell casing. This battery offers the advantages of being lightweight and very flexible. It can be molded to fit a lot of different configurations that aren't possible with the standard lithium-ion battery. As far as drawbacks go, both tend to be pricey because the custom shaping and custom molds can be especially difficult to manufacture, and even more so on a large scale. This diagram here to my left really documents the yin and the yang that is experienced within the lithium polymer batteries. One side, you have the desire for a high electrical output and demand. Meanwhile, the other side, that has to counterbalance with the inherent desire to be safe and the ability to squeeze into small areas now that we're seeing technology get smaller and smaller. Here we have a polypropylene carbonate polymer chain that was infused with a lithium compound, and it's now been formed into a very thin gel structure. As you can see here, this has been made to create a LiPo battery in a very small configuration that's able to provide an electrical current. Finally, we can compare the three different types of batteries that have been discussed so far. We have the lithium-ion battery with the liquid electrolyte, which is what you would typically go buy at this grocery store today. And then you have the two lithium polymer batteries that we discussed also. One with the solid polymer electrolyte and the other one with the liquid electrolyte, but the polymer casing around it. Since the lithium-ion battery with the liquid electrolyte and the polymer casing lithium polymer battery operate in the same basic manner, only one's encased in metal and one's encased in the polymer, they have the same electrical output capabilities. Meanwhile, the solid gel polymer electrolyte, it's working there, almost quite the same level, but we're just not quite there yet. After the break, I'll send you over to Willie, who will tell you about the research efforts that are going on with lithium polymer batteries today.
Welcome back. There's much interest in LiPo batteries as high-performance power supplies, specifically in consumer electronics. And due to this, there's been many research efforts throughout the world to advance LiPo batteries, including national projects such as USABC in the US, NITO in Japan, and Joule in Europe. Lithium polymer research extends here at Penn State also. Professor Chaoyang Wang is involved in research in lithium-ion battery technology and polymer electrolyte fuel cells. He's the director of the lithium-ion battery manufacturing laboratory here at Penn State, where researchers are able to manufacture automotive batteries from raw materials. This gives them the freedom to vary the constituents and interior structures of the battery, allowing them to improve performance, cycle life, and cost. It's the only facility of its kind at a U.S. university, so we're very lucky to have it here. Recently, Professor Wang published an article in Nature for a design for a self-heating lithium polymer battery, which has the potential to overcome one of the largest problems facing lithium LiPo batteries, which is low temperature performance. Lithium polymer batteries are a technology that still has yet to be fully developed. There's still a significant amount of research that needs to be done. The main areas that this research is involved in improving is increasing the energy density of the batteries, improving the high rate discharge performance at low temperatures, improving the capacity recovery after long periods of standing without use, and decreasing the extent of self-discharge, and increasing the cycle life performance of the batteries. Increasing the energy density of lithium polymer batteries is one of the most important aspects for them to become effective as portable power supplies. There are many different ways to go about doing this, some of which include increasing the filling density of active material by using a compressive filling process, use of high-capacity active materials such as polysulfides for the positive material and metallic lithium for the negative material, and achieving higher packing density. You can achieve higher packing density by taking advantage of inherent safety and the leak-proof nature of lithium polymer batteries to minimize the packing size. Increasing the low-temperature performance of LiPo batteries is extremely important if they're ever to become practical for use in automobiles, high-altitude drones, or other electrical devices that will experience low temperature. The key to improving the low-temperature performance is reducing the interfacial impedance between the active material and the electrolyte. Some of the key ways to do this are the modification of the active material surface and improvement of the electrolyte composition. This could include the addition of a low molecular weight polymer for dry polymer electrolytes, or increasing the ratio of solution in gelled polymers. Other ways of reducing the interfacial impedance could include increasing the active material surface area, prevention of the formation of reaction products on the interface, and use of gelled elastic polymers to compensate for expansion and contractions with temperature. Batteries are required to recover their full capacity after long periods of time without being used. Currently, some capacity is lost in LiPo batteries after not being used for a while, and this is something that will need to be corrected in the future. Also, the decreasing the self-discharge rate of LiPo batteries will also need to be addressed in the future. Currently, they have relatively high self-discharge rates relative to liquid electrolyte, which will need to be improved. And increasing the cycle life of the battery is essential for all batteries. Currently polymer electrolyte shows a life cycle performance that is comparable to that of the liquid electrolyte, but it's a feature that is continually improved for all batteries. Now we'll go to Jesse with more information on the future of LiPo batteries.
Thanks, Willie. So we just learned about current research being done in LiPo batteries, but what's next? Today we are faced with choices. It's hard to have all of our LiPo batteries work at room temperature, but research says polymers in salt or polymers in molten salt might actually be the solution. We're also faced with the choice of either more power or energy, or the choice between high performance, which is achieved by heating the polymer, or the choice of flexible material, which is used in gel electrolytes. So unfortunately, we're faced with a choice, but can we have both? Research has shown that improving these problems, we need to improve dry solid polymer electrolytes. This can be done by enhancing the mobility of the polymer chains and increasing the carrier density. Will just talked about this, but even more, to improve our future, we need to improve the design. One major future for LiPo batteries will be its use in improving wheelchairs. Current electric wheelchairs run very slow and are very heavy, but with LiPo batteries, they would actually take up a third of the space, be 6 times lighter, and help with speed. And they're actually very cheap and easy to get a hold of. The reason they're not being used right now is, as Nate said earlier, the polymer casing makes it very flexible, but it also makes it very easy for them to be punctured. This means that if they are damaged at all, they can actually cause a fire for the wheelchair. Also, they need to require a special charger, which is shown in the picture. When the LiPo batteries are in series, they all have to be charged with this charger to the exact same voltage. If they are not charged to the same amount of energy, then they can actually cause a fire. Another look into the future for LiPo batteries is the future of large battery farms, specifically in California through the Advanced Microgrid Solution and Tesla. These battery farms are expected to be about the size of 5 parking spaces and be used during major power grid peaks. With these battery farms, they are expected to save up to 25% of energy with only being placed in 24 buildings. By the year 2020, it is expected that they will save 1 gigawatt worth of energy, which is equivalent to one large gas-powered nuclear plant. These power peaks normally occur during hot summer days when air conditioners are on full blast. Tesla lithium-ion polymer batteries used to just be for cars, but not anymore. As mentioned before, the large battery farms will fall under their new product called power packs. These power packs will be used for utilities and buildings to power large amounts of energy. They also came up with a new product called Powerwall. These are small devices that can actually be mounted on homeowners' walls and be used during power peaks or emergency backups. They can either be used to power entire homes or select utilities. The way these power packs are used is they conserve energy. This can be done through solar energy and be used and stored up in the power pack battery and used when needed. Next, we will hear from Matt about how lithium polymer batteries are currently being used in our everyday lives.
Many companies across the globe manufacture lithium polymer batteries. Some of these companies include 3M Automotive, Electrochem Solutions, and Polaris Battery Labs LLC. These are large manufacturers that create the batteries and sell them to the smaller companies to be used with their product. Some companies, however, do their own research with the batteries to better specialize the battery for their product. Due to this, there are a wide range of applications that can be used with lithium batteries. They can be used in a wide range from hearing aids to mobile devices to cars. In mobile phones, a lithium-ion polymer battery is used by companies such as Apple, Samsung, and Motorola. The batteries need to be small and flexible to fit inside the mobile device. They only contain one cell, which provides roughly 3.7 volts. This is a big upgrade from the 1.2 volts provided by other batteries they used to use. In laptops, a total of 3 cells is typically used, giving 11.1 volts. For RC toys and drones, a lithium polymer cell is used. The reason for this is they have a high discharge rate, providing quick accelerations for either the car or the drone. They are especially desirable in drones because they are lightweight, giving more flight time hours. Depending on the size of the drone or car, a total of 6 cells can be used. Typically in helicopter drones, a flight time of 10 to 30 minutes can be achieved, while airplane drones have a total of 60 minutes. One area where LiPo batteries are making a big impact is in the electrical vehicle field. They are used by companies such as Toyota and Tesla. Last year, Toyota redesigned their Prius model using lithium-ion batteries and cut a total of 20% of their body weight. This provides for longer distances for driving. Tesla also has many different designs of cars using the lithium-ion batteries. They come in 40, 60, 70, 85, and 90 kilowatt-hour batteries. They require a large amount of cells to achieve the power. In the 90 kilowatt-hour battery, a total of 8,650 cells are used. Each cell provides around 3 to 4.1 volts, and with a full charge, it can travel up to 250 miles. In conclusion, there are many different styles of lithium-ion polymer batteries. They have many different functions and are more versatile and efficient than other batteries. As the technology and research grows, the possibilities for these batteries are endless. Thank you for your time, and I'll see you next week on 15 Minutes.